Thank you very much, Nate. Thank you to all my collaborators, and thanks for Google for sponsoring a part of the trip to the US. So I would like to talk about CryptOpt, which is our approach to generate high performance and high assurance assembly. Let's get started. So when we take our typical off-the-shelf compiler and try to compile our library with it, for my laptop, for example, we see that the performance is not always what we want. And even worse, sometimes it introduces bugs, which, especially for cryptographic libraries, is a big But it's not too surprising because compilers are general purpose. They can do a lot of things. We can compile almost everything with it. And on top of that, we can also compile for everything with it. So it makes sense that the compilers are not perfect at everything. So let's see how we typically solve that problem. On a scale where we consider the performance and the ease of reusability, we have the generic C version on the lower right-hand corner, which provides a lot of reusability, but not the performance that we want. We can then start parameterizing the C code for different primitives or specializing for different CPUs. But the highest performance is achieved by just handwrite the assembly in the machine's assembly language. Not only do the first three options not give us the performance that we want, we also need to trust the entire C compiler toolchain to not introduce any bugs. Whereas for the handwritten assembly, that trusting computing base is much smaller. With our tool CryptOpt, we're trying to push that border to the upper right-hand corner. And this is where we think we landed. We generate code, performance-wise on par with handwritten assembly, very easy to use, and our trusted computing base is very small. So let's see how we did that. Again, our idea comes from two main observations. One is that the compilers are general purpose. However, some code is very special. And with special, I mean actually much simpler. For example, these algebraic expressions, which do not contain any control flow. So in this work, we're trying to answer the question, how can we exploit this simplicity in order to improve performance and correctness? So our idea is, instead of compiling to fast code, we want to search for a fast implementation. And in the second step, we want to prove it correct. I will now go into detail on how we search for the fast implementation and then quickly sketch how we prove it correct. So our search algorithm is a little bit like what a first-year student would do. Start off writing some code that does the job, and then randomly modifying it to see whether it's faster. So then the student would run the code, and if it's faster, keep modifying at other random places, see what happens. And if it does not improve the performance, just undo that last modification that we've just done and try something else. In professional terms, this is called a random local search. We start somewhere random and then randomly try different things and explore the neighborhood for better candidates. So to see that in action, I brought an example. So let's put our optimizer on the left side, and the first step is to just write some code. Assuming the variables x, y, and z are somewhere in memory, first step is to add x and y together. Multiplying by z, compute z squared, and add all of that together. So this is our scheduling. Now the second step is to choose instructions that actually implement these operations. And we do that by attaching instruction templates to these operations. So what it means is that the first addition operation is implemented using the ADCX operation, the multiplication with the mulx operation, and so on. Now, to generate the code, we just read from top to bottom, gluing these templates together, and the glue is what we see in black there, which is just some instructions which move the data into the right spots, so our template actually works. So we see that we have the blue ADCX instruction and some glue on top in black. And similarly for the other instructions, and this is how we get our first code. The next step is to modify the code. And we do that by modifying two distinct operations. So one is the instruction scheduling, in which we just change the order, and the instruction selection, so the template that we associated with it. So let's start with changing the operation order. And the question is, which operations can I reorder? Well, I can reorder everything which is not data dependent. So for example, we see that the middle multiplication operations do not share any gray arrow, so there's no data dependency, so we can swap these around. So let's do that. We see that the code changed a little bit. The red instruction is now at the bottom. So we have a different assembly version which implements the same thing, but it's slightly different. And now we run these two things on our target machine and see whether it's faster. And let's say that in this case it's slightly faster for some bizarre reason, and we can modify something different. And our optimizer then randomly chooses a operation, for example that add operation up there, and replaces that ADCX template with something equivalent or semantically equivalent. So for example, we can use the add instruction for that. And we see that the clear carry instruction then changes into, well, nothing. And we have another assembly program which implements our function. And now we run that again, and so on. So with that, we can gradually improve the performance. And if we do that many, many times, the performance graph could look like this. So we have our evaluated modifications on the x-axis and the speed up over a Clang compiled baseline on the y-axis. So we see that we start off a little bit slower than our baseline, and we end up with an assembly program which is around 60% faster than what Clang would have produced. Okay, so now that we have our optimizer, we need to feed it with some program which exploits or which has these algebraic properties. And for that, I would like to introduce Fiat cryptography. Fiat cryptography is a framework which is able to synthesize new code from functional programs. All it needs is some cryptographic parameters, for example, a prime number, and it can then materialize these functional programs into code, for example, C, Rust, or Go. Okay, so now that we have Fiat cryptography on the left side and our optimizer on the right side, all we need to do is glue them together. So we feed the proven correct Fiat code into our optimizer, and out comes the fast assembly. So let's see how fast we can get. So in our field study, we generated code for the multiply and square operation and compared that against GCC and Clang for these primitives that we see in that table. So filling out this table, we see that, for example, for the curve 25519 multiply, we can generate code which is around 19% faster than what Clang would have produced. And this is an average over 10 microarchitectures featuring AMD and Intel processors. And filling out the rest of the table, we see that that trend continues, that on average, for most of these things, we can improve the performance. Okay, so now that we have field multiplication or field arithmetic optimized, the much more important operation in cryptography is a operation called the scalar multiplication, which internally uses the field multiplication that we've just optimized. So for that, we did another study, and we see on the x-axis different implementations for the scalar multiplication. And on the y-axis, we see the cycles which the microarchitectures need to implement this operation. So lower is better in this case. Especially on the right-hand side, we see the blue and black bars. And that is, we replace the field operations inside of OpenSSL, which is hand optimized. We replace that with our optimized version, and we can see that on average, we can match this performance, which is impressive. Even better, if we look at only the latest architectures, for example, the Intel 12th and 13th generation machines, we see that we can even outperform the handwritten assembly. And that is not too surprising because the handwritten assembly could not yet adapt to the whatever Intel did to improve the performance in their processors. But we can just press a button, wait, and out comes fast assembly. Okay, so now that we have our fast code, what about correctness? I promised that as well. Coming back to this overview graph, we could either prove the entire optimizer correct, but this is a lot of work, and we opted for something simpler. So instead of validating the translator, or the optimizer correct, we just validate the translation correct, and that is the assembly. So we implemented a checker which gets two inputs. One is the fiat IR, which is proven correct, and the assembly which is supposed to be implementing this IR. This checker features two symbolic execution engines, one for the IR and one for the assembly. It then executes these programs symbolically and checks whether the output is the same. And if it is, then the assembly indeed implements that fiat IR that it's supposed to be implementing, and our code is provably correct. And with that, we get an end-to-end proof from the functional program, which is proven correct once and for all, through all these modifications which are proven, down to the assembly. So let's quickly summarize. We turned the compilation of cryptographic code into a search, and we used a random local search heuristic as our heuristic and used the runtime as our cost function. And the result of that is that we now have proven correct assembly for the field arithmetic used by produced by fiat cryptography, now with on-par performance for hand-optimized assembly. And two little success stories as well. We have introduced the Curve25519 code already in Boring SSL, which is Google's SSL library, which is used in, for example, Chrome and Google's backends. And we're working on getting the optimized code into the Bitcoin Core library, which uses our code for their block signatures, improving the formal assurance and the performance a little bit. And with that, I can leave you with that QR code, which links to our GitHub repository and links to the papers. And you can try out CryptOpt running on your own machine for your favorite prime or for your favorite machine. And now I'm happy to take any questions. Thank you.
Just to remind folks online, we have a Discord channel, and we'd love to have questions from the virtual participants. There's a thread where you can type your questions.
So I'm Samuel from UNSPSL. On your table about performance, there was one case where you had worse performance than GCC and Clang. This was due to certain architectures that were bad, but some other you were better than those competitors. Do you know why? In this case, it was worse.
So we did not really look into why exactly this is worse. It is very fluctuant in sometimes the shape of the prime is just bad for our optimizer to use, but we haven't looked into that too much.
Thank you.
Thank you.
Hi, I'm Dave Holland from Galois. I was wondering how you measure whether things are faster. Like you do it by running it, I take it?
Okay, so the question was how we measure the performance of our code?
How you measure the performance as you're running the optimizer.
Okay, so we actually implement this assembly strings, we assemble that into memory, and we then run randomly to get rid of any biases of location in memory. So we randomly measure them and then just take the cycle count.
Okay, fair enough. Have you thought about any way that you might be able to cross-compile, like using models instead of the actual current hardware?
So we tried using models, but these models are not fine-grained enough and they're not realistic enough. So we tried modeling, but the result that we get is just too flat for us to optimize. Yes, we do get a little bit of noise into our optimizer, but every wrong decisions of keeping or not keeping a modification can be reverted in a subsequent modification attempt. So it's not that detrimental for a wrong decision to have made. But we need to decide on something, and some noise is actually quite good for that.
All right, thanks.
Thank you.
Just a quick logistic point. If speakers could speak into the mic clearly, the acoustics in this room are not the best.
Hi, Manya, undergrad from Stanford. I was wondering if you have any numbers for how long it takes to get to the optimized version. And I was also wondering in particular if you tried checking after each code modification as opposed to the whole program at the very end, and whether there's some speed up associated with sort of this incremental checking versus this complete check.
Okay, so the first question is, how long does an optimization take?
Yes.
Okay, that depends on the size of the function. We have functions, very small functions, in the range of hundreds of instructions. That only takes half an hour to an hour, depending on how long you want to run the optimization. Other implementations range from hundreds to thousands instruction, and that takes around 2 hours, depending on the machine and the architecture that you run on. And the second question was, if we consider...
I was wondering why you ran the checker on the complete sort of optimized program as opposed to running it after each modification and just throwing the program away if it failed the checker?
Yeah, simply because it takes time to run it. And we don't need to check every modification that we do, because every modification is supposed to preserve the equivalence. But supposed to, we're not sure about that. Hence, we implemented that checker, which gives us the formal guarantee of actual correctness.
Sure, thank you.
And maybe just a little add-on, in practice, this checker always returns correct. It is just for formal assurance and during development when me try to do something more fancy and that breaks stuff. Thank you.
Hi, I'm Wei Hang from Apple. So is it possible or beneficial to use this random optimizer in conjunction with existing backend optimizations, such as instruction combining and scheduling in LLVM?
I did not quite get the question. Are you asking whether this optimizer could be used as an LLVM backend?
Or rather, like as additional passes in LLVM, or yeah.
Theoretically, maybe. The question is, can we run the code? Probably not. If we have models, sure. But the question is, how good are these models for our architecture? If we know exactly how the architecture works, then a model could be sufficient and detailed enough to guide the optimizer. So then, yes. Does that answer the question?
Yeah, because I guess the thing is that your optimizer is like directly from IR or to assembly, which kind of slips over the entire backend.
Okay, the functions that we get from fiat cryptography is already in an SSA form, and it's very close to assembly-ish. So it is close to LLVM. We also had an LLVM parser as a proof of concept to show its flexibility. So yes, it works on LLVM, I guess, if that's sufficient as an answer.
It's okay.
Yeah, just talk to me afterwards. Yeah, thank you.
Great. We have one question from Discord. I'm very excited to have a virtual question from Charles Averill. They ask, were there any other search options tested instead of the local random search?
Yes, so in fact, one problem with random local search is that we don't necessarily optimize to a global optima. And for that, we actually use a bet and run technique where we start off with a lot of different spots in our random search space. And after some time, we choose to only use the most promising one and continue optimizing that. There may be other heuristics, but we wanted to keep it simple for now, and it works surprisingly well. There may be better options, and you're welcome to try them out. Yeah, that's pretty much it, I guess.
Great. While Jingbo's getting set up, I'll ask one more question. So fast code is great, but in crypto, we often care about other properties of the code, such as timing for side channels. Have you thought whether this approach might be useful for generating code that has other properties besides being faster?
Okay, so our optimizer just calls this "is it faster" function, and that could be anything really. It could be does this modified assembly use less stack space? Is it smaller? Does it use less power? You can measure whatever. And if we consider the side channel security, yes, it is side channel secure because the code that we get from fiat cryptography is already side channel secure, and we do not optimize with any optimization techniques or passes that hamper that. So we keep the side channel security, the timing, at least the timing security. Yeah.
Okay.
Thank you very much.
Let's thank Jill again.